So today is going to be redox. So we kind of saw that in the video. We're going to talk about oxidation and reduction and what that means. We did the oxidation numbers first because you have to be able to recognize your oxidation numbers on both sides of the equation to see if there is a change. Again, what's in your notes is in red, so that's what goes in your blanks. Normally when we balance redox reactions, we do this with the half reaction method. The good news is for you guys, we're not balancing them in regular chem. So we have to recognize what's oxidized and what's reduced, but we don't actually have to go and balance the redox reactions. First one is oxidation. The video referred to that. It is the loss of electrons. And of course, remember when I'm losing electrons, I'm going to be losing things that are negative, so my oxidation state will become more positive, okay? In terms of metals or nonmetals, metals are going to be oxidized. So your metals will, free metals, let's just say that, free metals will be oxidized. They're more likely to be oxidized. Now, if it's already got a charge, it can very well be reduced. But a free metal, meaning it's nothing bonded with it, will be oxidized. So if I have, say, sodium free metal, it's going to be oxidized. It's going to lose electrons. Okay. Now, if I go back to a free metal, that's different. That would be reduced. But if it's a free metal by itself, it's going to most likely be oxidized. Reduction is the gain of electrons. And because I'm gaining things that are negative, my oxidation state is going to become less positive or more negative. And the reason I say less positive is because let's say I've got something that's going from a +7 to a +2. It's clearly gaining electrons. It's gaining 5 electrons. But it's still a positive number. And so sometimes if I say more negative, kids get a little bit confused in their head and they're looking for a negative number. So it becomes less positive is the way we look at it. So this is just an example of sodium and chlorine reacting to form sodium chloride, and we're just breaking out what's being oxidized and what's being reduced. In this case, sodium's going from a 0 when it's a free element to a +1 when it's in the compound, so it's oxidized. And then the chlorine is going from a 0 in the compound to a -1, so it's being reduced. Okay, and we could do this all at once by assigning these charges over here and seeing that that's what's happening. And that's what you'll do to figure out if something's being oxidized or reduced. And that's just putting it back together, and then that's for when we have to balance it. But since we don't have to balance it, we can skip over that. But this right here is a very good way to remember which is which. And that's oil rig. You can use Leo the Lion goes grr, but I always use oil rig, and that is oxidation is loss, reduction is gain. This unit is real heavy on acronyms to help you remember that, but I highly suggest you use them so that when you're looking at it, you don't get confused over which is which. Oxidation is loss, reduction is gain of electrons. Okay? When we're trying to figure out if something is an oxidation-reduction reaction, best thing to do is assign all the oxidation numbers on both sides of the equation and see if there's a change. If there's not a change, then it's not going to be an oxidation-reduction reaction. For instance, if I had an acid-base reaction, let's say I was doing NaOH plus HCl, and it makes NaCl plus H2O. If I were to assign oxidation states, this is a +1, +1. -2, +1, +1, -1, -1, +1, -2. Nothing is changing, so this would not be a redox. Okay? But let's say I was doing sodium plus magnesium chloride. Then I would assign oxidation states, and I would see that this is 0 plus 1. This is +2 to 0. That would be redox because the change in the numbers. So that's how we recognize if something's going to be redox or not. We've got to look quickly. Okay. If you see something that's got free elements on it, then it's going to usually free elements on one side and then a compound on another. It's usually going to be a redox. Okay. The agents, we have reducing agent and oxidizing agent. They are opposite, okay? If something is oxidized, it's the reducing agent because it causes the other thing to be reduced. If something is reduced, it's the oxidizing agent because it causes the other thing in the equation to be oxidized, okay? You will never have what's oxidized being the oxidizing agent, okay? You cannot have oxidation without reduction. They both have to be present, okay? So whatever's oxidized causes the other thing to be reduced. That's why it's the reducing agent. They're exact opposites, okay? And then, so in this case, that's the equation we looked at a while ago. We had said earlier that sodium was oxidized, so it is the reducing agent. And we said chlorine was reduced, so it's the oxidizing agent. Okay? Now, in this case, we have free elements both times, so we would just say chlorine is the oxidizing agent, sodium is in the reducing agent. If that element was bound up in a compound, we would actually list the whole compound as being the reducing agent or the oxidizing agent. We're going to do one of those in a minute. Did you have a question? Oh, I thought you had a question. So this is in your notes, this little visual of if whatever's oxidized causes the other thing to be reduced, so it's the reducing agent. So they never are the same. They're always going to be the opposite agent. We don't have to balance, so we can skip that. But we are on this one. This is a left side activity, I believe, for you. But we are going to practice on saying what's oxidized, what's reduced. So the element that's oxidized oxidizing agent, the element that's reduced, and the reducing agent. Okay? So if I look at this, I've got to figure out what the charge of my manganese is in this compound. What's the charge of manganese, or the oxidation state, rather? Huh? No, the overall charge of the is +7. For the manganese is +7. The fact that oxygen is not appearing on the other side, because we're not balancing it, don't be alarmed by the fact that it's not, because if we were to balance this, the oxygen would reappear, but since we're not balancing it, we're not going to worry about the oxygen. So, and then the iron's already assigned. So iron is going from a +2 to a +3. So is it gaining or losing an electrons? Gaining? It's losing. It's getting more positive. So it's lost 1 electron. Okay? So manganese is going from a +7 to a +2. Did it gain or lose? Gained. How many did it gain? Gained 5. Okay? So when we go back to oil rig, oxidation is loss of electrons. So the element that is oxidized is iron. Okay? The element that is reduced is the manganese. Okay? That's the element that was reduced. So if iron was oxidized, the Fe, the iron, is going to be the reducing agent. Okay? If manganese was reduced, the compound that it was in, MnO4, is the oxidizing agent. That is technically correct. If you had put manganese was the oxidizing agent, I probably would still give you credit for that. But technically, it's the actual permanganate because it's in there together. I didn't just stick manganese in there. I stuck permanganate in there. Okay? So technically, this is the correct answer. But if you just put the manganese was the oxidizing agent, I'd probably go ahead and give you credit for that. Okay? So that's how you're going to do the practice problems. And we'll probably have to refresh our memory since we're doing a lab tomorrow. And then that brings us to practical applications. So some of the reactions we've already studied, like combustion and all these, some of those are actually redox reactions. Okay? They're just a type of redox reaction. Like I told you a few minutes ago, anytime you see a free element, like here, here, and here, and it's a free element on one side and it's bound in the other, it's going to be a redox. Because this is a 0, and it's having to change when it goes into a compound. So if I know that there's a change in my oxidation state on one side or the other, then I know it's a redox. Okay? If there's not a change, like we saw with that acid-base reaction, then it's not going to be a redox. Okay? So your combustion reactions are going to all be redox because you're starting with elemental oxygen and it's going into a compound. And then single replacement are going to be redox because you're starting with an element and a compound. So that element, if it goes into the compound, is going to be, usually if it's a metal, it's going to be oxidized. And then some synthesis and some decomposition. Okay? And the reason we say some, in the case where we're doing two elements into a compound, definitely going to be redox. But sometimes we have two simple compounds going to a more complex, and those may or may not be redox. You just got to look at the oxidation states. Okay? So that brings us to electrochemistry, which is how a battery works. And what we're going to be doing tomorrow is our electrochemistry lab. Okay? Electrochemistry is any conversion between chemical and electrical energy. Okay? So basically, you didn't realize when you're using your phone, it's electrons that are driving that reaction, right? That phone. Nerve impulses in your body, that's what made that frog leg move, because the metal, whatever that was. What are those things called? Scapula. I could not think of that. I was thinking spatula, and I knew that wasn't right. But the metal scapula had conducted the current to the nerves in the frog's leg. Corrosion, electroplating, that kind of thing. I don't know why that is on there twice. I think I just wasn't paying attention when I did that. The reduction potentials is something you just need to be aware of. You do not have to have any of them memorized, but they are published values, and you can figure out when you have a reaction how much voltage that it would produce, or in the case of a non-spontaneous, how much voltage I would have to supply to get the reaction to happen. Okay? So that brings us to voltaic cells, also called galvanic cells. Both are correct. We usually use the term voltaic cells. They are for reactions that are spontaneous, meaning that will happen on their own. I don't have to put a power source into them, okay? And it always will generate a positive voltage, okay? And, of course, from the video, Volta was the Italian scientist where we get that unit for. When you're talking about a voltaic cell, the anode is where oxidation occurs. We remember that by saying anox, okay? The cathode is where reduction occurs, and we remember that with red cat for reduction in cathode. There's a salt bridge, which allows the ions to flow. In the case of the video, that was the material between the copper and zinc that Volta did. That would be a salt bridge, and then your electrons are always going to flow from the anode to the cathode. The way we remember that is fat cat, because your cathode will get bigger because the electrons are going to flow to that direction and the metal will be deposited. So when we do our penny lab, your penny will actually be the cathode when we do that one tomorrow. Okay. Here is a picture that you have in your notes. Notice that in a voltaic cell, your cathode is positive because cations are positive. That's the way to remember that. And, of course, that's where you would write red cat over there. I would write it down so you can remember that. Red cat is where reduction takes place at the cathode. These are very helpful acronyms for a test. Very helpful. And then on the anode side, I would write anox for anode and oxidation. And then notice that the electrons are flowing from the anode to the cathode, and that's the fat cat, because eventually the cathode would get fatter and get bigger. Okay? The voltmeter is just there to measure the voltage that is produced by this particular reaction. This right here should be, whoops, I didn't hit the thing. This should have been flipped because they're showing it as a reduction, and it needs to be shown as an oxidation because that's where oxidation is occurring. So I would flip that and do zinc 2+, and then yield zinc plus 2 electrons. And those 2 electrons are which are going around here and then coming over here, and it's causing this to be reduced, and then the copper would plate onto the cathode. Okay, and then of course if I was to take out the salt bridge, the reaction would cease happening because the salt bridge helps to balance out the ions. And then of course some examples are your car battery. The hydrogen fuel cells is another example. And then your batteries that you use in your phone, in your remote at home. That's why they have to be eventually replaced, because there's only so much juice, so to speak. Of course, the one in your phone is rechargeable. Some of you probably have rechargeable batteries in your remotes. Does anybody use rechargeable batteries like that at home? I think they're just a pain, so I just buy new batteries, but yeah. So electrolytic cells are the opposite of voltaic. They are for non-spontaneous reactions. So when you are using your phone right now, it is in the mode of a voltaic cell. When you plug it in and charge it, now we're doing the reverse. We're doing a non-spontaneous reaction, and so for that to happen, we got to add an electric source. We got to add power to it. So it's going to usually be in the source of a battery. Also, this is going to be in a single cell system. Your oxidation is still occurring at the anode, so it's still an ox. Reduction is still occurring at the cathode, and the electrons are still flowing from anode to cathode. The difference is now the cathode is a negative. I thought I hit that. Your cathode is negative and your anode is positive. So that switches on an electrolytic cell. In the case of tomorrow, this is what we'll be doing. We're actually doing an electrolytic cell. It's going to look kind of like this. We're going to have the battery, and it's going to be a zinc electrode, and then, of course, instead of a spoon, it'll be your penny. Okay? And we'll hook up the battery. It's going to be those 6-volt batteries, those little big ones like that. And we're going to have the zinc plate onto the penny. So electrolysis is an example of electrolytic. That's how we can break water down back into hydrogen and oxygen. Some practical uses is electrorefining, where they'll take an ore and they'll purify it by doing this electrorefining process by putting a power supply in there. And then this is going to go on page 186 in your left side activities, and you need to write down the differences between voltaic and electrolytic cells. It's a good thing to study. One thing that got left off of there is for voltaic, you've got a positive cathode and a negative anode. In electrolytic, it's a negative cathode and a positive anode. So the polarity of the electrodes switch. Okay? So write that down on page 186. Even if you're not doing your notebook, you should still write that down because it's a good thing to study for the test.